Hi, I'm Callum Stevens.
And I'm Luke Pritchard Cairns.
We're part of the Quantum Ordering Group headed by Professor Andrew Huxley at the University of Edinburgh. We'll be talking about a recent publication from our group into the composition dependence of the superconducting properties of uranium-tellurium-2, written with our postdoc Chris O'Neill and Andrew. Uranium-tellurium-2 was discovered in work by Sheng Ran, Nicholas Butch, et al. At NIST to be a heavy fermion paramagnetic unconventional superconductor, with a zero-field superconducting transition at 1.65 Kelvin. Recently, field reentrant superconductivity above 40 Tesla was seen in a study by Ran et al. A split transition under the application of pressure was seen in heat capacity measurements by Braithwaite et al., suggesting multiple superconducting states in the phase diagram of uranium-tellurium-2, and a residual heat capacity Sommerfeld term in the superconducting state has been observed universally, shown here in a measurement by Imago et al. The residual Sommerfeld term equaling approximately half the normal state value, along with NMR results, have motivated suggestions that half the electrons form equal spin Cooper pairs. Similar residual heat capacity was observed in other unconventional superconductors, such as uranium-platinum-3 and strontium-ruthenate, but was sensitive to the growth conditions of these materials. We decided to investigate how the chemical vapor transport growth conditions of uranium-tellurium-2 affect the superconducting properties. Details of the growth are seen in the diagram. We varied ratios of depleted uranium to tellurium and found a corresponding change in the stoichiometries of samples measured by energy dispersive X-ray analysis, as can be seen in Table 1. Growth A has a similar TC to previous samples produced by other groups, while growth B with an above stoichiometric growth ratio produced non-superconducting samples. These replicate previous studies' results. Growth C of an intermediate ratio was found to have the highest superconducting transition temperature, and we will focus on these samples comparing to samples reported elsewhere. Lowry X-ray diffraction can be used to orientate single crystals from each growth, and these could be fully indexed with the reported orthorhombic structure for uranium-tellurium-2. The EDX analysis uses X-ray emission from scattered electrons close to the sample surface to deduce the composition and relative amounts of elements, with an estimated probe depth of 0.3 micrometers. Several line scans were taken across the surface of samples from each growth, approximately 1 millimeter in scale. An example is shown in the image. These values may be subject to systematic error, but the relative measured ratios give an indication on how the growth ratio affects the stoichiometry of crystals formed. Shown is a comparison of the low temperature resistivity for crystals from growth A and C compared to data from Ran et al. And Hayes et al. The C sample has the highest ambient pressure TC reported for a uranium-tellurium-2 crystal. Additionally, the high temperature resistivity of the growth C sample shows a lower Kondo coherence crossover temperature than that reported by Ran and Hayes. Not shown is the resistivity from a sample from growth B. We observe no superconductivity, but instead an upturn in resistivity occurring at 750 millikelvin, and we suspect this may be the result of a structural reordering, but we are investigating this further. These results suggest to us that there is an optimal composition for growing samples of uranium-tellurium-2 to enhance the superconducting properties. Luke will now discuss samples from growth C studied by heat capacity, compared to data reported in the literature.
Thanks, Callum. So, motivated by the EDX and resistivity measurements, we have measured the heat capacity of 3 samples from growth C, which, to be clear, was the growth which showed the highest superconducting transition. From this figure, it's clear that all 3 show similar behaviour and a superconducting transition at 1.77 Kelvin, which is the highest of any uranium telluride compound to date. Note that this is slightly lower than the TC observed in resistivity. Based on the composition dependence of the superconducting properties, this suggests, perhaps, that sample C5 has a slightly different composition at the surface as compared to the bulk, and by extension, that it might be possible to grow a sample with bulk TC as high as the 2 Kelvin observed in resistivity. We then analysed the data using this purely phenomenological function, from which various parameters could be determined, as shown in this figure. We used this same function to fit the zero field heat capacity data from a number of different studies, some of which are shown here in comparison to our own data. The parameters for all sets of data are shown in this table. Three things are immediately obvious. Our samples have the highest TC, have the largest superconducting jump, and have the smallest Sommerfeld coefficient, all of which are clearly linked to differences in composition. This next figure concentrates on the low temperature portion of the specific heat and features only those sets of data which go low enough in temperature to show an upturn. In the majority of studies, this upturn is fit well by a Schottky anomaly, which may be attributed to the interaction of the uranium-235 quadrupolar moment with a crystalline electric field gradient. For our samples, this interaction gives a reasonable energy splitting of approximately 50 millikelvin. Importantly, however, all but one sets of data, including the higher temperature data, are adequately fit by a t-squared term plus a constant. This constant is the aforementioned residual Sommerfeld coefficient. This residual component is observed to be approximately half the normal state value, which has motivated some to suggest that only one spin direction is being paired. However, if we plot the ratio of the normal state to the residual Sommerfeld coefficient against Tc for all samples, we see that the two are negatively correlated, which argues against this interpretation. As Callum mentioned, the same correlation has been observed in other unconventional superconductors and has been linked to impurities or defects. These act to smear out the features of the superconducting gap and leave a residual density of states. Our EDX measurements suggest that the same interpretation might be valid for UTe2. Specifically, the suppression of Tc as well as the enhancement of the residual Sommerfeld coefficient may be linked to tellurium deficiencies, which might lead to, for example, planar stacking faults or point-like defects. As we approach the stoichiometric compound, the superconductivity is enhanced before being dramatically suppressed, potentially as a result of a structural transition. Finally, we observe a similar correlation between the residual Sommerfeld coefficient and the size of the jump at the superconducting transition. The simplest way to link these two parameters is to assume that only a fraction of the sample is superconducting, and therefore fit to this function. This gives A equal to 2.76, as compared to the BCS value of 1.43. This indicates strong coupling, but we acknowledge that this analysis might be a bit simplistic. So here are the main results of our study. We have demonstrated the composition dependence of the superconducting properties of UTe2. We've exploited this to grow crystals with the highest superconducting transition temperature to date. In the majority of studies, the low temperature upturn observed in the specific heat may be explained by a Schottky anomaly, potentially from the U235 quadrupolar moment. And we've shown that there is a negative correlation between the residual Sommerfeld coefficient and Tc, both of which vary as a function of tellurium content. And finally, all of this has been discussed more thoroughly in this paper, recently published by our group, a link to which is in the description. So with that, thank you for listening to our talk.
Thanks for listening to our talk.